Let's start. So, we are studying orthogonal decomposition theorem. So the basic setting is as follows. So we are given a particular subspace W, okay, and then also we suppose we have the orthogonal basis of our subspace, and that bases are these are U1 through UP. Okay, so these are orthogonal set, and they are spanning this the given subspace W, and then we are given any vector y, so that may or may not be inside of our subspace W. Okay, but in general, let's suppose this W is not exactly inside of the subspace W. Okay, and then this given vector y can be decomposed into two parts, where the first one is belonging to our subspace W, which means that this first part called H hat, this guy is represented as a linear combination of our bases. So given those basis vectors from U1 through UP, so this one is having a form of a linear combination of these basis vectors. Okay, and then we have the remaining part called Z. Okay, and we want to satisfy one additional condition, that this Z should belong to W perpendicular, which means this vector Z should be perpendicular to any vector in our subspace W. Okay, so again, this Z, after obtaining this y hat, and then so of course Z is y minus y hat, which can be viewed as a remaining component, and that component should be perpendicular to any vector in W, and that condition is equivalent to those conditions that this Z is perpendicular to each of our basis vectors. Okay, so there are infinitely many number of vectors belonging to subspace W, but this C should only be perpendicular to a finite number of vectors, which are our basis vectors of the subspace W, which are U1 through UP. Okay, so in other words, we are decomposing the y into the sum of these two vectors, y hat and z, where y hat is belonging to the given subspace W, and z is perpendicular to our subspace W. Okay, so how do we obtain this y hat and z? We first formed a just general linear combination of U1 through UP for our y hat. So this one, this entire equation or representation is corresponding to y hat, right? And then this y hat should be perpendicular to subspace W, which means that this guy should be perpendicular to U1 and U2 and so on, right? And then once we form this inner product, once we form the inner product, and then so this guy and the inner product with this guy, and it will produce some non-zero, but this guy, if we compute the inner product between these two, we know that U1 and U2 are perpendicular to each other, or orthogonal vectors, and so it will produce a zero inner product. So all the remaining parts will just produce zero, and the only one part, which is about this U and C times U1 and U dot, the U1 dot U1, which is the inner product between itself. So I'm talking about this green part, I mean inner product between these green parts. Okay, and that should be this guy, y hat times u yeah. So this guy should be y hat, right? So I think I made a mistake over here. We need a y hat here. So I try to obtain C1 through Cp by equating or building up this kind of equation. But yeah, I think I made one little mistake where I thought this y as y hat, right? So y hat is not decided. And so let's see. Yeah, so let me just change the direction of the proof slightly. So let's suppose y hat is given already in this form. Okay, so yeah, someone already gave you the linear combination coefficients as those values, and then yeah. Yeah, sorry, but yeah, I think I was right. Yeah, so so yeah, we want to build up the equation that this y minus y hat, which is our z part, right? This z part. So this z should be perpendicular to any vector in subspace W, and in other words, this y minus z should be perpendicular to each of our basis vector. And so yeah, we build up this kind of equation, right? Right. And then the first part, y dot u1 is coming from here, and then y hat dot u will be this guy, right? Yep, that is right. And so yeah, c is obtained yeah as follows, right? Okay, so likewise we can obtain c2 and C1 through Cp in this manner. Okay, so we obtained these linear combination coefficients, okay, that satisfies this y minus y hat. Okay, again, y minus y hat is perpendicular to our subspace W, right? Okay, such a linear combination of these u1 through up are have this kind of form. Okay. Okay, and then now at the last part of our lecture, in the last Tuesday's class, we discussed briefly about their existence and the uniqueness. So we now want to discuss whether this kind of a decomposition, or the question is, does this y hat always exist such that y minus y hat, which is equal to z, which is this green part, is perpendicular to our subspace W. Okay, so does such a y hat always exist? And also another question is that if it exists, and then is it unique or not? Okay, so that is our question. Okay, so we can easily answer the existence question as follows. So we basically started with y hat being equal to C1 and U1, C2 and U2, and so on, right? CP and UP. And then we had no problem of obtaining C1 through CP, right? So we didn't assume any additional thing. So we just need any given vector y and any given particular set of basis vector of U1 through UP, right? So as long as they are orthogonal vectors or orthogonal basis for our subspace W, and then we can always represent this linear combination. This linear combination representation, which is our y hat. So this once you just compute this y hat in this by following this equation, and then you can always obtain this solution y hat. So it always exists, right? So during the process of obtaining this equation, there is no additional assumption that stops us from obtaining this equation. So we can guarantee that it always exists, which means that once you obtain this y hat by just following this formula, and then the remaining part of this z is always perpendicular to our subspace W. Okay, so we answered this existence question. Okay, and then now let's think of some uniqueness question. So uniqueness question can be proved as follows. So given a particular y, suppose you have a two different representation or two different forms of these decomposition. So you initially have this this particular decomposition where this y hat is defined by this formula, right? And then suppose you have another different representation or another different vector of y1, which is called the y1 hat. Okay, and then in this representation, how do you obtain z? So there is no specific formula or there is no additional thing to do to obtain this z. Z is nothing but y minus y hat. So you only need to compute y hat, and then you just subtract it from y, and that's how you obtain this vector z, right? And so here, if we assume that we can obtain another vector y hat, which is called the y1 hat, and then so let's just equate these two, okay? Because these two are all y, so we can represent them in this manner, and then in this representation, we also need to satisfy this y hat should belong to W, and this z1. This is y1 hat, and z1 should be also belonging to W perpendicular, right? So that's our initial assumption. Okay. So the question is whether we can find this y1 hat satisfying these two. Okay, and this y1 hat should be different from this y1 y hat. Okay, and then from here we can manipulate this equation into this form, right? We just moved this guy into the left, and this guy was moved to the right. Okay, 네. 어디요? 네, 맞아요. 그 강의 자료에는 횟수로 나와 있죠. 그죠? 이래가지고 네, 아이패드 싱크를 안 맞췄군요. 네. 오케이. So it should be y hat, right? 오늘 뭔가 아이패드가 배터리가 없어갖고 급히 백업 아이패드 갖고 와갖고 네, 정신이 없었네요. Okay. So by looking at this equation, we can observe one interesting fact. Hopefully, that this guy is what? Y hat is belonging to W, and Y1 hat also belong to W, right? And then it can be viewed as the linear combination of these two vectors, where those two are all from W, right? And so we just linearly combine those two vectors belonging to the same subspace, and that linear combination should be still belong to W, right? Because why is that? Why is that? Because of the basic definition of the subspace. Because subspace should be closed under the linear combination, right? And so these two are just a linear combination of the two vectors belonging to W, right? And so this part should be still inside of W, right? And then likewise, this C1 minus C, each of these two are belonging to W perpendicular, right? And so W perpendicular itself is a subspace. And so this guy should be belonging to W perpendicular, right? So the left representation belongs to W, and right representation belongs to W perpendicular. And what is the definition of W perpendicular? This guy. So if we pick up one vector from this subspace, and then it should be orthogonal to any vector in W, right? So so here these two are the same vectors, and the same vector, their inner product should be 0, because the right one should be perpendicular to left one, and they are essentially the same vector. And that, let's call that same vector as maybe V, and then this V from the left should be perpendicular to the same vector V on the right, right? From the definition or the condition of this W perpendicular. Okay, and then we know that the inner product of the same vector is 0, and then that vector should be just a 0 vector, right? And that means it should be just a 0 vector, and thus y hat should be y1 hat. Okay, so that means those two vectors should be identical to each other, and so it violates our assumption that this y1 hat is another different vector from y hat. Okay, so that way this y hat is uniquely determined, and thus z is also uniquely determined as well. Okay, so again the conclusion is that this orthogonal decomposition is always unique. Okay, so this y hat is always uniquely determined, and thus accordingly z is also uniquely determined. And here more intuitive explanation or understanding is that, as I briefly mentioned in the last lecture, what is y hat? What is the meaning of y hat? So y hat is something like this, and first in Korean, what was it called? It's 이거 저기 수선의 발이죠. 이거 어떤 subspace 어떤 점에서 이제 어떤 subspace로 수선의 발을 내리면 그 수선의 발은 언제나 그러니까 항상 존재하고 그게 항상 uniquely 이제 determined 된다는 뜻이고요. So I'm not sure about the proper translation about it, but yeah, it's called a foot of perpendicular vector. I'm not sure. Okay, but if you think of y, and then if you imagine this y hat, where this y minus y hat, which is this vertical vector, that is perpendicular to any vector in W. Okay, so that vector y hat is always uniquely defined. Okay. Okay, so this was this orthogonal decomposition theorem. And these are our little exercise, and we are given y, and we are given two vectors, u1 and u2, which spans our subspace W, and then these two are orthogonal vectors because their inner product, if you compute their inner product, and then it is 0. Okay, and then we can just use this formula in order to obtain this y hat, which is our 수선의 발. And then if we want to compute this z part, okay, z part, after computing this y hat, we just subtract it from the original vector y. Okay, so this is z, and from here, this c, okay, should be perpendicular to what? Y minus y hat, right? So, yeah, yeah, z is itself is a y minus y hat. So z should be perpendicular to what? u1 and u2, right? So, yeah, you can verify this by just computing the inner product between this z and u1, which is this guy, and also the inner product with u2. Okay, and then also, yeah, another a special case that we can think of is that what if our vector y is already inside of our subspace W? Okay, so in this case, so y is, yeah, so in general, this subspace is much smaller set compared to the original space, where maybe suppose our original space is R3, and then suppose this subspace W is spanned by the two vector, and thus its dimension is just 2. And then in general, y is not belonging to our subspace W. Okay, but what if our y is already inside of our W? Okay, so in that case, y is somewhere here. And then what is orthogonal projection? Y hat. So that would be just the same point, right? And then this vector z will be just a 0 vector corresponding. Okay. Okay, so in that case, if y is belonging to subspace W, and then y will be y hat, right? Which is the orthogonal projection onto W. Okay, let's move on to the next theorem, which is the best approximation theorem. So yeah, it is quite understandable intuitively. Yeah. So let's look at the theorem. So we are given a vector y, which is not necessarily inside of our subspace W. Okay, and then we consider this a y hat, which is our orthogonal projection of y onto this W. Okay, and then this part, y minus y hat, which is our z part, and then we consider the norm of this z, okay, the norm of z. So here, and then we consider another vector v, which is belonging to our subspace w. Okay, y hat is also belonging to w, and we consider any other vector v, which is also belonging to this w. Okay, and then if y hat is an orthogonal projection, and then the norm the norm of this y minus y hat is the smallest possible value. Compared to the case where we chose v for any other vector inside of our w. Okay. So that way it's called this y hat can be viewed as the best approximation of this y through our subspace w. And let me just give a hopefully a little bit more intuitive understanding about it. So what do we mean by this approximation? Okay, approximation. So we want to so we are initially given this vector y, okay, and then we want to represent this vector as another vector. Okay, so we want to find the some approximation of this y vector into another vector. Okay, and then suppose that vector was this guy. So this is our maybe y tilde, which represents the approximation of y. And then how can we measure or how can we quantify this approximation between this y and y hat? We can just simply think of their distance, okay? Because we represented this point approximately as this point, and then what is the amount of the error? Okay, that error can be measured as the length between these two. Okay, the distance between these two vectors, right? And then of course, if if this y tilde can be placed a little bit closer to y, and then this y tilde, okay, this guy is a better approximation than this y hat. This another y tilde, right? Because this distance is shorter. Okay, and then now we want to add one more constraint that our approximation, like this y tilde, should always belong to our subspace w. Okay, so we don't want to approximate this y vector to any other vector somewhere in this space, but we want to constrain this y tilde, which is our approximation of y, so that this y tilde belongs to our subspace w. Okay, so we can only pick up this y tilde from our subspace w. Okay. Okay, then suppose we pick up y tilde over here. Okay, and then so here we have an origin, and then this one is y tilde, and then what is the error, amount of the error? So that is the length of these, or the distance between these two vectors, right? Okay, and then we can consider another y tilde over here, and then the error will be here, right? And then here, the main point of this theorem, of best approximation theorem, is saying that your y hat, which is the orthogonal projection, is the best approximation. Okay, when this y hat is belonging to this the subspace W. So in other words, if we decide this y hat as our approximation of the original y, and then the distance of this part will be smallest, okay, among any other chosen vector maybe as another approximation belonging to subspace W. Okay. And let's briefly look at the proof about it. So suppose you pick up any other vector v as another approximation of y, and this v is also belonging to W. Okay, and then what is the error vector? So error vector is this guy, y minus y hat, and that's the first error vector. And then the second error vector is this y minus v, right? And then the question is the distance or the length of this vector and y minus v. So length of this vector, is it like this or this? So which one is shorter, has a shorter length? Okay, the one with the shorter length, and that will be considered as a better approximation, right? And then from here, so we can always think of this this kind of triangle, right? So the first one is the error component from y hat, and then another one is the second error component from v. Okay, and then what about this y hat minus v? Okay, this guy, which is this vector. Okay, so this vector, we can notice that this vector is still belonging to our subspace W. And why? Because it is just a linear combination between these two. And y hat is belonging to W, and v is also belonging to W, right? And so their linear combination is still belonging to W. And then we know that y minus y hat is belonging to W perpendicular, which means that this y minus y hat, so this part, is perpendicular to y hat minus v, because this one is still belonging to W, and this guy should belong to W perpendicular, which means that this vector is perpendicular to any vector in W, right? So that means those angle, okay, this angle is always 90 degrees because their inner product is 0. Okay, and then for whatever vector v that you choose inside of the subspace W, you can form this this triangle, and that triangle will always have 90 degree in this angle, right? And so you will always have this triangle with the 90 degree. Okay, and then we can use the Pythagorean theorem here. Okay, so in other words, this guy, okay, like y minus y hat squared plus y minus v squared should be equal to y minus v squared, right? So I just applied the Pythagorean theorem, right? Okay, and then each of these components will always be non-negative. So it will be either 0 or positive, right? And so what if we remove this part? Okay, so that is always non-negative or greater than or equal to 0. And thus, if we remove them, if we remove it, and then this guy will be smaller than this guy, right? And so our conclusion is that this length, okay, this length is always smaller than this length. Okay, but then when do we achieve this equality? Okay, when do we achieve this equality? That's when this removed part is 0. Okay, so in that case, y hat should be equal to v, right? Which means that if we choose v as y hat, and then yeah, that's when, yeah, we can achieve this equality. But it's just nothing but choosing the same vector, right, in the place of v, right? And then if we choose v as the different point from y hat, and then this part will be strictly positive value because y hat and v are different vectors and their distance will be non-negative. I mean, their distance will be strictly positive, and thus, yep, this one is greater than 0, and in that case, this one is strictly smaller than this guy. Okay, so this claim or this relationship is always true for whatever vector v that we choose from W, right? So that way, yeah, we prove that this guy, okay, when choosing y hat as your approximation, and then in terms of the length of this error vector, that y hat will be your best approximation of y, okay, compared to any given, any other vector v that are chosen from subspace W. Okay. Any questions? 네. 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 네, 프로젝션, 그러니까 올소그너 프로젝션이 아닌 경우는 예를 들면 이런 평면이 있고 이 점을, 그러니까 프로젝션은 그냥 단순하게 그냥 뭔가 약간은 그림자라는 뜻이거든요. 프로젝션이라는 말이 영사기 뭐 이런 거 혹시 기억하나요? 기억하는 게 아니라 나도 모르니까, 네, 나도 잘 모르니까 이게 뭐 이렇게 필름 해갖고 이렇게 빛을 이렇게 해갖고 뭐 이게 사실 프로젝터거든요. 이게 영사, 네? 아 이거, 네, 그러네요. 네, 그렇죠. 저것도 프로젝터, 그렇죠. 저것도 프로젝터. 근데 아니 뭐 저건 아마 저 물리적인 뭔가 이렇게 필름을 가지고 이렇게 하는 건 아니고, 이제 우리가 뭐 이렇게 필름을 이렇게 대면 이제 여기를 딱 투과시키면 이게 뭐 어디는 이제 가려지고 어디는 이제, 그게 이제 프로젝션의 개념이어서 여기서도, 그러니까 프로젝션은 그러니까 뭔가 이제 빛을 쏘고 뭔가 이렇게 막혀서 생기는 저기 상 혹은 그림자 같은 개념이에요. 그래서 이제 여기서 이제 빛을 쏘면 이제 뭐 태양이 뭐 이런 식으로 뭐 해가 여기 있다. 네, 뭐 빛의 방향이 이렇게 된다. 그럼 여기가 이렇게 돼갖고 여기가 프로젝션이에요, 사실. 네. 네, 이것도 프로젝션이고, 근데 이제 우리가 올소그너 프로젝션이라고 그러면 해가 딱 이렇게 머리 위에 딱 있어서 여기가 이제 수직일 때 이게 이제 올소그너 프로젝션인데, 올소그너 프로젝션이 아닌 경우를 우리가 따지느냐, 거의 안 따진다고 보면 돼요. 네. 그래서 그냥 프로젝션이라고 하면 그냥 올소그너 프로젝션으로 생각을 하면 될 것 같아요. 네. So even though we can consider any I mean non-orthogonal projections, yeah, but those non-orthogonal projection is not much meaningful, at least in the academic literature, and thus, yeah, when talking about the projection, and then we usually, yeah, refer to the orthogonal projection. Okay. Any other question? 네.
y는 y hat 플러스 z로 나눌 때,
네.
이게 y가 만약에
네.
w 안에 있는 경우에 z가 0벡터가 되니까
네.
y hat이랑 z가 수직인 건 이해가 가는데,
네.
y hat 개념이 수선의 발 같은 개념이에요.
네, 수선의 발.
근데
네.
그게 y hat이 y랑 같아지는 경우가
네.
평면 안에서는
네.
느낌상 그걸 수선의 발이라 말할 수 있어요.
아, 그냥 자기 자신인데 뭔가 내린 게 아닌데요. 뭐 내릴 게 없긴 한데, 그래도 뭐 그냥 정의상으로는 그것도 그냥 뭐 수선의 발이라고 우리는 생각을 해요. 그리고 그냥 뭐 다시 말하면 수선의 발은 정확하게 올소그너 프로젝션이랑 똑같은 얘기고요. 네, 그 다음엔 뭐 그냥 원래 그 스페이스에 있는 애는 수선의 발도 그냥 자기 자신이다라고 그냥 이야기를 하는 거죠. 혹은 그냥 아까 여기서처럼 그게 이제 어디 있었나, 그 올소그너 프로젝션, 네, 이 자기 자신이다 이런 식으로.
어떤 명세에서 이제 y에 대한 프로젝션을 하면 그
네.
결과인 y, 그 결과로 나온 y 값은 항상 y에 대한 수선의 가리다라고 말해도 그거라고 말할 수 있어요.
다시 한 번요.
그러니까
네.
프로젝션 y,
네.
y 햇이
네.
항상 y에 대한 수선의 가를 한다라고 해서
예.
저 동일한 경우에도 그거라고 말해요.
네, 그렇죠. 네. 그러니까 저게 만족하면 걔는 그 안에 있는 거냐? 그 서브스페이스 안에 있는 거냐?
그 명세가 항상 참될 수 저렇게 같은 경우에도 예외 없이 될 수 있는.
그러니까 저게 만족하면 y가 그 서브스페이스 안에 있느냐? 그리고 그게 항상 참이냐?
y 햇을 수선의 가리라고 무조건 말할 수 있어요.
y 햇을 그러니까 이렇게 구한 거? 요렇게 구한 거요?
네, 그래서 y가 이제 더블 밖에 있으면
네.
당연히 수선의 가리인데
네.
이제 만약에 참형대를 따지려면 예외가 하나도 없어야 되니까
네.
y가 w 안에 들어간 경우에 이제 자기 자신을 만들어도
네.
그 명세 예외 없이
네, 그렇죠. 그러니까 자기 자신이면 일단은 요식을 구할 수가 있죠. 그렇죠? 그러면 z가 0이 나오잖아요. 저 에러 텀이 저 z인데 어떻게 보면 저 z라는 게 아까 여기서 그 에러의 길이가 돼요. 여기 best approximation theorem에. 그렇죠? 그럼 저게 이제 0이 나올 거고. 그렇죠? 그럼 저 0벡터는 w perpendicular 안에 포함되는 애냐? 그렇죠? 그거를 만족하면 이 올소거너 디어렘을 만족을 하는 게 되겠죠. 왜냐하면 이 올소거너 디어렘은 하여튼 y를 두 부분으로 분해하되 이제 y 햇은 w 안에 있고 z는 w perpendicular 쪽에 있는. w perpendicular가 아니 여기 w가 이제 0이 나왔다. 그 말은 이제 그냥 0벡터가 w perpendicular 안에 들어가느냐 아니냐를 생각할 때 들어가죠. 왜냐하면 이제 subspace는 0벡터는 무조건 포함을 하니까. 네, 그래서 이제 그것도 예외 없이 만족을 하게 돼요. So yeah, this theorem is always true regardless of whether your y is already inside of w or w being outside of w. Okay, I mean y being outside of w. So yeah, if w is inside of the y is inside of w, and then this z will be zero vector, and that zero vector is still belong to w perpendicular, and thus this theorem is still holding true, right? 네.
어프로시메이션에서 원래는 부등호가 작거나 같아야 되는데 y 대신 v가 아니라는 가정을 하고 그렇게 하는 거지.
그렇죠. 네.
원래 그런 가정이 없다면 작거나 같다가 맞는 거예요.
네, 그렇긴 하죠. 네. 네. 근데 이제 V가 Y 햇이 똑같아진다는 거는 뭔가 우리는 두 개를 좀 비교를 하고 싶은 거예요. 이제 지금 올소거너 프로젝션이 이제 하나로 딱 특정한 이제 하나로 정해졌고 우리는 어떤 다른 V를 이 subspace W에서 어떤 거를 뽑아도 이게 하여튼 best approximation 이 길이가 하여튼 다른 애 그러니까 이 V를 Y 햇이랑 다른 애로 뽑으면 저거는 무조건 등호가 성립이 안 되는 거예요. 그렇죠? 그 말은 다른 애 누구를 뽑든 내가 이긴다는 뜻이에요. 내가 이렇게 동점 이렇게 비기는 경우도 없다 이거예요. 네, 하여튼 내가 유일무이한 승자다 이거예요. 공동 1등도 아니고. 네. Okay. So yeah, in this theorem, if you choose this v as a different point from y hat, and then this inequality is strictly holding, by having this inequality sign over here, not including this equality sign, right? And also it's related to the fact that your orthogonal projection is uniquely defined, okay? So if you have another different orthogonal projection, and then you may have a kind of a different point that has the same smallest possible error values. So in that case, you can think of having multiple best approximation of y, right? but that's not that's not our case. So yeah, because simply because our orthogonal projection is always uniquely defined. Any other questions? Okay. And then you can if we look at the second example, it's also quite simple and straightforward application of what we just learned. So we are given y and u1 and u2, and then what is the best approximation point that belongs to the subspace W spanned by these two orthogonal vectors. Okay, and then we can just simply compute this projection of y onto subspace W. So that is your best approximation. Okay, and you can also compute the amount of the error, right? So this is our z vector, right? So the length of this vector is your, how much the error has, right? How much errors we have, right? So if we compute the norm of this y minus y hat, and this one, it's just this length, right? This length. So that length is what? Let's see. So that length is 3 times the square root of 5. Okay. So that length is the smallest possible length in terms of the error, right? So when you pick up any other points in W, and then the difference or the distance between this v and y, okay, that will be always greater than this value of 3 times square root of 5. Okay, then let's move on to theorem 10. And then we considered orthogonal projection when given on orthogonal basis vectors. But what if we are given orthonormal basis vector of a subspace W, right? So it was quite trivial to change orthogonal set into orthonormal set, because we just simply scale each vector so that the vector length is all ones, right? So if we are given orthonormal vectors over here, and then how do we compute the orthogonal projection? Okay, orthogonal projection. So that orthogonal projection, back to this formula that we have here, and in case the lengths of u1, u2 through up are all ones, and then this part, okay, so u1.u1 and up.up, and those are all ones because simply they are just the unit vectors, right? And then this formula becomes quite simple, right? Because this part will only contain this part, right? The formula becomes quite simple, right? And that simple formula is represented is represented as this, right? And so initially we had u1.u1, right? And then we no longer have it because our u1 is a unit vector. Okay, and then from this formula we can do a little interesting trick over here. So in this case, let's understand this formula in this manner. So we compute the inner product between a given vector y and the first orthonormal vector u1, right? So we basically compute the inner product between these two, and then that inner product can be represented as follows. So this and this and this one is y transpose, and this one is u1, right? Yeah, that is just corresponding to this inner product, right? From the perspective of a matrix multiplication, because y transpose can be viewed as 1 times maybe n, and then this one is n times 1, right? And then we can freely change, yeah, we have no problem of switching the order between them, right? And so let's just represent it as this guy, u1 transpose and y. So yeah, the inner product satisfies this commutative law, right? Okay, and then this guy overall is generating a scalar value, right? And that scalar value is further multiplied by this u1, right? And then can we represent it as follows? So we further apply commutative law again. So u1, and yeah, let's just call it as a star, and this star can be placed in the right hand side. I mean on the right. It is multiplied on the right because it doesn't matter, right? Because it's right, and this scalar is the same as this part. Okay, and then we just change it these order of this multiplication, and then let's just put this star using this, okay, and that part is becoming u1 and u1 transpose, u1 transpose, and our vector y, right? Okay, and then this was the inner product, right? That produced a scalar, which is our star here. Okay, and then here, can we change it into this form? u1 and u1 transpose and y, and we just put the parentheses over here. So from this manipulation, initially this part, we just perform the inner product and then produce a scalar value. And that scalar value is multiplied with our column vector u1, right? But in this part, we first perform the outer product between the same vector u1 and u1, right? So u1 and u1 transpose will produce this big matrix of n by n, right? And that n by n matrix, which is formed by this outer product between u1 and u1 transpose, and that will be further multiplied by y, right? Okay, so this calculation or this computation is exactly the same as this part or this guy, right? Okay, and then this one is u1, yeah. So we have this guy, and then we also have this part, right? And so, yeah, I'll just keep writing this formula by manipulating, by applying this kind of manipulation, and then there's a u2 and the u2 transpose and y, right? Okay, and then the sum of these two can be written in this form: u1 and u1 transpose plus u2 and u2 transpose and y, right? So we first form the sum of these outer product, okay? Sum of these outer product, and once we form that outer product matrix, and then we multiply this column vector y on the right, right? And then this part. Yeah, we already studied this form as one of the four perspectives of a matrix multiplication. So this guy will be in this form, U1 and U2 as our first matrix, and then the second matrix will have U1 transpose, U2 transpose, right? So that was that was represented as sum of rank 1 outer product. Yeah, when viewing our matrix multiplication, right? So let me just show that example. Okay, from this slide, right? So when having this outer product where we have a column vector and the row vector multiplication, and yeah, if we apply that into just the general matrix multiplication, and then we first pick up the first column vector and then first row vector on the right, and then form the outer product first, and then by picking up the second column and the second row vector, and then form the second outer product matrix, and then we just sum them up, right? So that is the same as this guy. And then now in this case, this part, yeah, we will rewrite it in this form. And then that is represented as follows. So if we have a matrix U which contains also normal basis vectors of our subspace W, and then this part times this part can be represented as U and U transpose and our vector Y, right? So this one is exactly the same representation, right? Okay, and then we can also view this guy as a linear transformation. So orthogonal projection. Okay, orthogonal projection is that, I mean, when computing the orthogonal projection of a given vector Y, and then you will have to apply kind of this kind of formula in order to obtain the orthogonal projection, right? And that orthogonal projection, I mean, when you have a orthonormal basis, and then this orthogonal projection is simply represented as this form, and then it can also be viewed as like a matrix and a vector multiplication, where Y, where this A is U and U transpose, right? So this U transpose, that matrix will be linear transformation matrix that will give you the orthogonal projection of any given vector Y. Okay. So yeah, in this sense, so this one is represented as a matrix multiplication with the vector, input vector, and that means this is a linear transformation of these vectors, right? So this this transformation is a linear transformation, which means that this satisfies this property of like forming the linear transformation first and then applying our transformation, and that result will be the same as just first applying the this linear transformation or this orthogonal projection first, and then do the linear combination later on, and then those results will be the same. Okay. So that means, so orthogonal projection, we have some kind of an intuitive understanding about this orthogonal projection. So we are given like a sun over here, and then it's just emits the lights, orthogonal to our surface, right? And then if we have one point, and then it's a shadow, will be our orthogonal projection, right? and then somewhere over here, so we have these 2 points, okay? And then we have a surface over here, which is our subspace, and then we can think of their orthogonal projection, right? And then suppose we are linearly combining these 2 vectors. So we have origin over here, and then we have these 2 vectors, right? So these 2 are input vectors. And then suppose we just linearly combine them into maybe another vector. And suppose we compute the orthogonal projection of that point. Okay? So that point is just a linear combination of first projecting these 2 into these 2 shadow points, and then linearly combining them, and that resulting shadow point, resulting linear combination point, that will be your shadow of this linear combination of these 2 original points. Okay. So that way, orthogonal projection is a linear transformation. Okay, and yeah, related to this case where we use orthonormal basis vectors. Okay, so let me just give additional explanation. So I'm not sure if we explained it already. So if I did already, and please stop me and let me know. And then suppose we have this U1, and we just consider the orthogonal projection onto this single line spanned by U1, and then our vector Y over here. Okay, and then so we want to obtain this vector, right? This vector, and then that vector. In order to represent or obtain that red vector, let's just think of the vector length and the direction. Okay, vector length and the direction. What is the length between them? I mean, what is the length of this vector and that vector? Yeah, so let's just utilize this characteristic of the cosine theta. So what is the vector length? So that is this guy, right? And then suppose we have a theta here, right? Okay, then it is this guy, right? It is this guy. And then let's just consider this y and u1, and that is y and u1 and cosine theta, right? And so in order to obtain this length, okay, when comparing it with this original inner product definition, it is just excluding this part, right? Okay, so this guy can be represented as this guy, y dot u1 and u1, right? Because this part is this part, right? Okay, so in this case we can understand this as follows. We first make our vector u1 as a unit vector, okay, having the length of 1. So if it has the maybe length of maybe 4, I mean is 4, and then maybe this guy. Okay, this guy is our unit vector that preserves the direction, and also the length is now just 1, right? And then what is the length of it? What is the length of it? Just compute, multiply this guy and cosine theta, right? And then this guy is now represented as this, right? Okay. Okay, so in other words, in order to obtain the length of this part, okay, the length of this orthogonal projection point, because that is y hat. The length is just inner product with your vector y and the unit vector. Okay, the unit vector of the same vector, same given vector u1. Okay. Okay, so that way we can compute the length of this guy. Okay. And then how do you represent the direction of it? The direction of it. So this is just the length. And then in order to obtain the vector, we need to have the direction. And that direction is, of course, this is u1. And then what is the vector that has the same direction, and also the length is just 1 because we just computed the length separately. Okay? We now we computed the length separately, and then we want to just extract out the vector that has the same direction but has the length of 1. And that vector is still, that vector is again this guy. Right? Right? So this guy is preserving the length, preserving the direction of u1, but the length is just 1, right? And then you can understand this part, this vector, as just a vector that contains the direction, but the vector length is just 1. And then we just computed vector length separately, and then we have the length and the direction, and then we can just multiply them together, right? And then it's like a y and the u1 and right. So this part is this part, which contains only the direction component, and this part is our this part, which only contains the length part, right? Okay, then once you rearrange it, the lengths will be multiplied together twice, right? And then y and u1 and u1. And then this guy is represented as u1 and dot product with the u1 itself, right? So I just wanted to show another way of deriving this orthogonal projection. Okay, so initially, if you remember how we obtained this kind of formula. Okay, how we obtained this kind of formula. So it was in this and the previous chapters, but let's see. Okay, so we kind of applied this way of proof or derivation. So we still represent y as y hat plus c, right? And then this c is y minus y hat. And if y hat, our subspace is spanned by only a single vector, and then the scalar it's a scalar multiple is our representation for y hat, and then this guy should be perpendicular to the original vector u, and thus we obtain this alpha in this manner. So I just showed another way of deriving this kind of an equation. Okay. By just computing separately the length component and the direction component. Okay, so here if we have just if we have a unit vector here, which means that we have the orthonormal vectors. Okay, orthonormal vectors. And then this kind of a normalization process of making our vector into a unit vector will no longer be needed, right? And this guy will be just u1, which is our direction component, and then the length component is just computed as y dot u1, right? Because u1 is already having the unit length, and thus this guy is our length component, and this guy is our direction component that already has the length component as 1, right? So you can understand this orthogonal projection equation, or this formula in this manner. Okay, so any questions? Okay, and then let me add one more thing over here. So we understand this U transpose Y as a kind of linear combination by just considering U transpose that matrix first, right? And still, we can also understand this in a slightly different manner. So we have this U transpose and Y. This is what we obtained, right? And then this guy can also be viewed as this guy. This is not that because this we are not representing an inner product. Yeah, we can represent it this manner, right? So in this case, yeah, so we are kind of computing this one first, right? And then rearranging them into a matrix vector multiplication. But anyways, yeah, you now understand this, right? And then in this case, we have U here, where we have maybe also normal columns, right? Also normal columns. And then what is this guy? So this guy is just a transpose and Y, right? And then this part will be just a three-dimensional vector where this guy and this guy will produce this guy, right? This guy and this guy will produce this guy, right? Okay, and that is corresponding to U1 transpose Y and U2 transpose Y because that is U1 transpose, U2 transpose, and so on, right? And then this guy can be viewed, yeah, so we have U1, U2, U3 here, and then these are multiplied with this matrix, and thus it can be viewed as a linear combination of these three columns, right? These three columns with the linear combination coefficient with these three, right? So yeah, so linear combination coefficients or weights can be obtained as follows, and then our ingredient vector or basis vector will be U1 through UP, right? Which are also normal vectors. Okay, so that's it for this third chapter, and yeah, also that's it for our today's class. Okay. So we have 2 more chapters to go before the end of the semester, and yeah, I'll continue the next chapter on the next Tuesday. Okay, thank you very much.